Okay, we are continuing with the same theme of performing hypothesis test in a linear model setup. Let us quickly remember the format that we have. So we had this, we are given that our data already fits the model y equal to x beta plus epsilon with the usual Gauss-Markov assumptions. Now we are also given some particular x naught such that column space of x naught is a subspace of column space of x, and we are asked to test the null hypothesis that x may be safely replaced by x naught. So that's the null hypothesis. The alternative hypothesis is this holds but this does not hold. So this is always given to us. This is the null hypothesis that we are testing. Now you have already seen this setup many times, and you have also seen that the geometric intuition goes like this, that you have this column space of x and we have the blue line which is the column space of x naught, and we saw that an ideal test should be based on this quantity RSS naught minus RSS divided by RSS, which is the extra amount of error, the extra error that we are incurring if we move from the general model to the null model, and we are measuring it in terms of the unit set by RSS, which is the acceptable level of error. So we have already seen the test statistic for our test, which is both intuitively justified as well as justified from the theoretical viewpoint as the likelihood ratio test statistic. Now in this video we are going to explore what is its null distribution. For that we are going to need the chi-square distribution, which is defined as this. If xi's are IID normal 0, 1, then their sum of squares is defined as chi-square, with degrees of freedom equal to the number of such xi's that we have. Now vectorially we can think of it like this. We have this x1 to xn, IID normal 0, 1, and then we stack them together to produce one vector x1, x2, xn. Then its norm square is precisely what we think of as the summation xi squared. That follows chi-square degrees of freedom n. So now n assumes that importance of being the dimension in which this vector is free to move. Now what happens if I replace my I with sigma square I, that is, we still keep them independent, but now their variance is sigma square. Clearly whatever we had earlier, that chi-square thing, will now be scaled up by sigma square. So I call the resulting distribution chi-square, sigma square chi-square is degrees of freedom n. By this I mean that when I say norm of x square follows sigma square chi-square n, I mean norm of x square by sigma square will follow chi-square with n degrees of freedom. What happens if I allow a non-zero mean? In that case the distribution, whatever that is, will be called the non-central chi-square distribution, and the non-centrality parameter we have taken as the norm square of the mu vector. Be warned here, it is not an entirely standard notation. Some authors will use something else in place of the non-centrality parameter, something like mu square, norms mu square divided by sigma square or something like that. There is no unanimity among authors as to which one should be the right right parameterizations. But we shall use this parameterization in this video.